Okay, homework help for rotation number 2. Okie doke, let's get started, shall we? All right, racing car travels on a circular track. Here's my radius. Oh, I ran my pen out. Man, that was in a hurry. I didn't expect that. All right, never mind. Okay, so we're given our radius of 260 meters. You are given a linear speed, so velocity, and you know what? Always be careful and take a look at the units as well. They should match. If you saw radians per second, you would assume it's an angular speed. But meters per second, that's a linear speed. All right, so you want to find its angular speed. That's a pretty quick application of this relationship. Okay, magnitude and direction of its acceleration. Hello, it's a circular track. You want to find your centripetal acceleration. And you can just use v squared on r for that. Really pretty straightforward. And notice again, the acceleration is given to you in meters per second squared. That helps you realize that they're not looking for an angular acceleration there. So that's a pretty quick one. Number 2 is a little trickier. Okay, you've got you've got a bicycle, and you've got a whole bunch of different measurements. Okay, so up here, that's what I would call the front sprocket, and then this little guy right back here on your diagram, that is the rear sprocket. Sprockets. I think that was an old Saturday Night Live thing, wasn't it? Sorry, I digress. So you're given also some diameters of the wheels and the pedal cranks. That's going to be a radius for you when you need it. Revolutions per minute. All right, so we definitely need that to go into radians per second. We've got another radius right there. And okay, so you want to change these for sure to meters, and you want to find the radius versus the diameter for all of those. So let's assume you get all of that done. Now you're ready to tackle A through D here. Calculate a speed of the link of the chain relative to the bicycle frame. Okay, well then, let's take a look. The linear speed of the chain is going to be dependent upon the front sprocket. That's the first thing to keep in mind. Okay, that's going to set the speed of the chain because that's where the foot is and it's going to be pushing on it, right? So if we're looking for a linear speed, notice the units are in meters per second. VT, or translational speed, is going to be the radius times the angular speed. Now, you know the angular speed because they tell you in the question, and you've done your converting, and the radius is going to be the radius of that pedal because that's what he's pushing on, right? So there you go. You should be able to, I'm sorry, I said that backwards. It's going to be the radius of the front sprocket. My bad. All right, so there you are with that. Calculate the angular speed of the bicycle wheels. Okay, now again, let's what we're going to figure is that the linear speed here for the chain, there's a reason they have you do the chain first. So that chain, of course, is going to travel from the front to the back. And so that tangential velocity from part A is going to be critical to solve part B. So once you've got that, you can, again, use the relationship r omega, except now, of course, you're changing the radius to the wheel itself because you want to know the angular speed of the bicycle wheel. So you want to use the radius that goes along with that bicycle wheel. Part C is calculate the speed of the bicycle relative to the road. Okay, so, and again, take a look at what you're dealing with in terms of units. This is meters per second. So we are looking for a tangential velocity here. What you want to know is, well, again, we're going to use something from previously, right? Part B has got an angular velocity. That is the actual back wheel, the big back wheel there. And that's what you're going to use to figure out how fast it's moving this way relative to the road. So times the radius of the larger wheel. And yeah, you should be good to go. You'll get that translational velocity. That shouldn't be too bad. Okay, I think you can figure out good old part D. Now, last question for this one. Disc thrower accelerates from rest, such and such and blah and blah. Okay, main things I'm going to remind you here, this is all kinematics that you're doing here. You're using all your different kinematic equations. But again, be careful. You want revolutions changed to radians. Let's see, we've got, that's already in in metrics. That's good. You're accelerating from rest, so you know your initial velocity is 0. You know your final velocity. Oh, sorry, my bad. Velocity. And this one, and you know how I know? Because I'm looking at the units. That's not an angular velocity, that's a linear velocity. Okay, but this, revolutions, that's theta. That's not, delta x. So don't get mixed up there. And then, of course, this is a radius. So final angular speed of the discus, well, yeah, we want that. Again, use a kinematics equation. You actually know quite a bit. This can get, this final velocity can get converted, again, because you have the arc, or the radius, I'm sorry, of your circle, and you should then be able to figure out that final velocity in rads per second, and it shouldn't be too tough to do, I don't think. I really don't. Determine the magnitude of the angular acceleration, assuming it is constant, so you're looking for alpha. You're going to use kinematics there, because you already know initial velocity. I mean, if it's 0 in a linear sense, it's 0 in a rotational sense too, right? And you know the angular velocity final. You know the delta x, or the delta theta, my apologies. You can solve for alpha, not a problem. And then the only piece you don't know is your time interval. So again, use a kinematics equation, use the values you already know, and you should be good to go. It's actually not too tough at all. All right, hopefully that was relatively helpful. And again, if you've got troubles, questions I haven't answered, or things that are still just kind of niggling at you there, let me know on Monday when I get back, and we'll start there.